giving you guys a heads up as to the first examination. Right? I believe that exam 1 is scheduled for not this Wednesday, but the following Wednesday. I believe that's September 21st. All right, so just giving you guys a heads up that 9 days is going to be our first examination. Essentially what I'm planning on doing is, next class we're going to work the majority of the predicates and quantifiers material. Monday next week, we'll probably finish up like a little bit of stuff that we have to do. I'll spend about a half hour for review and answer your guys' questions that you guys might have, and just outline like what to expect to see on the examination.
Just give the exam easier than the homework.
Just make the exam easier than the homework.
11A and B were, I think 11B was quite difficult.
Sorry about that. Not everything can be really easy. Sorry. All right. And what I did was, I think I posted an exam review for you guys, so use that as like a model as to what's going to be on the examination. Those are just old test questions. Okay. So questions before we get started, guys? Everybody okay with what to expect? Okay. All right. So let's go ahead and start by our different number bases. Okay. Generally, there's when we talk about computer science, there's 3 main number bases that we have to be concerned with. Okay. The decimal system is really an imperfect system when it comes to computers because it's not a power of 2. Okay. For some reason, we adopted it as humans because we feel it's the easiest one to utilize. Okay. But basically, guys, in a decimal system, you have digits 0 through 9, so there's 10 digits. Each of the digit places a power of 10. Okay, so you guys can see in the example that I have up here, and also on your guys' worksheet, that if I looked at the number 9,734, you multiply 4 times 10 to the 0, and that's the power. Okay, 7 times 10 squared, because this is the 0th, the 1st, the 2nd, and the 3rd power. So basically, guys, each of the different decimal places or digit places holds a power of 10. Okay. The same thing is true with the binary system, okay? Except there's not digits 0 through 9, there's only digits 0 and 1, okay? So binary just means 2. All right, so basically you guys can kind of think as to why computers work off of base 2. Because if you guys look at it, what's the only things that are in binary? 1 and 0. Well, that's exactly what trues and falses are, right? And that's why we've been doing this Boolean logic stuff, okay? So kind of think of like binary as sort of like the numeric way as computers think. They think of like ons and offs, impulses on and impulses off. Okay? Just like we did with base 10, each of the digit places is multiplied by a power of 2. Okay? So if I had the digit 100010, and I'm looking at this highest 1, this 1 times 32 is why it has a value of 32. Okay? All the other places except for the second place has a power of 0, because every time you multiply that power of 2, it just goes to 0 anyway. Okay? All right. Most people are pretty good with those two, and most people are pretty good with hexadecimal. Okay? Hexadecimal has 16 characters. Okay? They go from 0 to 9, and then they also go from A to F. Okay? In hexadecimal, A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and then surprise, F is equal to 15. Okay? So when you guys see those letters, just think of them as representing values for those. Okay? In computer science, we like to chunk things as much as possible. Okay? So think about how tedious it could be to write something like this. Like the number 34 twice. Takes 1, 2, 3, 4, 5, 6 character places. Okay? In base 2, things like 1,000 get really big really quickly. So what we like to do is we like to chunk things into 4 bits. Okay? And that's actually something called juxtaposition, where what we're going to do is we're going to figure out each of the 4 bits at one time and just turn it into hexadecimal. Okay? For those of you guys that are programmers, okay, how many of you guys have ever run a C or C++ program or any program, and it just goes into an infinite loop, and eventually, like you hit like maybe all control delete or whatever, and it says like core dump, and it gives you like this crazy string of like characters. So anybody remember seeing that? That's actually the physical location in memory where it ran out. Okay? Because that's what a core dump is. You just run out of memory, and the computer stops processing. All right. So and you probably see it like says like BEEF 1003 or whatever it is. Okay. That's literally the computer's way of saying, this is where my computer program ended, nothing else I can do. All right, so go there in that physical location in memory, which we can't find, because there's literally trillions of places. Okay, so does everybody understand like how these work and how they're related? Okay, basically, hexadecimal is a convenient way to write binary. Okay, it's just a shorthand way to write it. Okay, decimal is the way that humans interpret numbers for the most part. Okay, so what we want to try to do is, for humans, we want to talk to computers. So for us to talk to computers, we have to convert between these two, and then get into the shorthand way. So I always tell people that, or students, I always tell them, like, if you can get the binary, the other two are easy. Okay, so binary is like your intermediary between the other two. All right, so let's just go through, and the types of questions I'm going to ask you are, I'm going to give you one of the number bases, and I'm going to give you a value, and you guys are going to convert to the other two. Okay, that's basic sort of stuff. Okay, so let's take a look at a couple examples of this. Okay, so I have this value right here. Okay, so 1, 0, 1, 1, 1, 0, 1. And then the subscript 2 means that I'm in base 2, which is binary. Okay? Because if you have a 6-year-old looking at that, or a 7 or 8-year-old, they're going to say, oh, okay, well, that's the number, what? 1,011,101, right? That's what they think. So we don't know if it's going to be in binary or hexadecimal or octal, although nobody uses octal anymore. Okay. All right. So let's say I want to convert this. Okay. Here's the way that I think about it. Okay. I probably should have written this a little bit bigger, but this is just one way to think about it. Okay. So I'm going to write the numbers like a little bit more spaced apart. And what I'm going to do is I'm going to recognize that each of those represents a power of 2. So this is 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 4, 2 5, 2 to the 6. Okay? Because that's what we said binary was, right guys? They're just each different powers of 2. Okay? Anything that has a bit or a digit of 0, I don't care about. Because when you multiply by 0, it's nullified. So this guy, right here, we're just multiplying these. Okay, that's all we're doing. So this is really 1 times 1. This is really 4 times 1. This is 8 times 1, bless you. This is 16 times 1. We skip 32, and this is 64 times 1. Okay? So that's all that really means, guys. We're just adding up the powers and the bases of 2 with this. Okay? Anything that has a 1, anything with a 0, we throw it away. Okay? So this just winds up saying that this is going to be 64 plus 16, which is 80, plus 8, which is 88, plus 4, which is going to be 92, plus 1, which should be 93 in base 10. Okay? And in our class, guys, when we're doing number conversions only, make sure you write which base it's in. Okay? So, now if it's something obvious, I'm okay with that. Like if I say specifically convert to decimal, okay, I get that, okay? But if we don't know, if I'm telling you to convert to 2 different bases, make sure you tell me which one it is, okay? So,
How do you know we're in base 10?
oh, well, what I asked you guys to do first was either convert to either decimal or hexadecimal, right? Anytime you're multiplying by the powers of 2, that's converting to the base of 10. Okay, so now I'll show you how to get to the other one in a moment. Okay, does that make sense, sir? This is just the process to go to base 10. Okay, other questions, guys? Okay, to be able to go to hexadecimal, let me show you guys how to do that. So I'm going to write the number out again. Okay. And I want you to notice what I'm going to do is I'm going to chunk these into 4s, starting from the right. So basically what I do is I write out the first 1, 2, 3, 4 bits, okay? And then the next 1, 2, 3, 4 bits. Notice that there's only 7 bits. So guys, just like you would do with any other decimal number, what we're going to do is we're just going to put our implicit 0 in front of it. Okay? So this is how we're going to hexadecimal. Okay? And guys, doesn't that make sense? Because hexadecimal has 16 characters, right? Well, 16 can be created from any permutation, or the numbers 0 through 15 can be created through any permutation of those values. Okay? Now what I'm going to do is just like we did up top, this is going to be 2 to the 0 plus 2 squared plus 2 to the third. Okay? I don't have 2 to the first because of the 0 in there. Okay. So does that make sense, guys? I'm only looking at the bits to where there's a 1. Okay? For the second set, we start back over. So this is 2 to the 0 plus 2 squared. Okay, because I don't care about the zeros right here. So basically every group of 4 is its own problem. Okay? Now, if I take 2 cubed plus 2 squared plus 2 to the 0, that's 8 plus 4, which is 12. 12 plus 1 is 13. But we don't want to write 13, right? Because we're going to be in hexadecimal. What are we going to write instead of 13, guys? D, right? And we know it's D because right over here, we said that 13 is represented by D. Okay? So this guy right here corresponds to D. Okay? Does that make sense, guys? We just go through and we chunk 4s. We figure out what the decimal representation is. If it's 10 or over, we just use this table right here. The good news is, this guy right here is going to be 5, right? It's going to be 4 plus 1 is 5. So this guy converts to 5. So our number in hexadecimal is going to be 5D, base 16.
Why is it base 16?
Because this is the process that we use to convert to base 16.
Okay.
Okay? So the first was our process to go to decimal. This is our process to go to hex, because we're chunking in 4s. Okay?
Okay.
And if you think about that, that's like, we can get any permutation of
So I
that.
just want to clarify now, every time we do something, say the procedure in the first step, it's going to be that number to the base 10.
Correct, right. This
We're
is
searching for base 10.
right.
And then
So
the second one we're going to base
right, this guy right here is to convert to decimal all the time, and this is the process
10.
hexadecimal. I probably should have been a little bit more clear about that. I'm sorry, guys.
The only reason is because on binary it specifies binary as base 2.
Oh,
But
okay,
here it doesn't
right.
say decimal system is base 10 or
Right,
hexadecimal is
okay.
base 16.
And that's because we started in base 2, so we're converting to
Got it.
base. Okay, Andre, go ahead, sir.
So what's the whole reason for having the letters, the system? Like what's the use for that? Why not just have it with numbers?
Oh, okay. Well, think about this. This is the number 93. Look how long this is. Look how convenient this is. It's much more convenient for us and for computers to start chunking things, okay? Just so that way we don't have like these ridiculously long bits that just take forever to read, okay?
So letters were just chosen because like that's
There's some here.
a
Convenient,
it's a
right?
solution.
That's exactly right. Okay, go ahead,
What if you get like a number that's like over,
15?
yes.
Won't happen. That's a good question. In case you didn't hear the young lady, she said, what happens when you get a number over 15 for those 4 blocks?
You always,
What's the biggest possible number we can get? It's 1, 1, 1, 1, right? That's 2 to the 0, 2 to the first, 2 squared, 2 cubed. 8 plus 4 is 12, plus 2 more is 14, plus 1 more is 15. You can't go any higher than that. That's a good question though, because some of us might be thinking, well then we just have overflow, which is why we never have.
so it should be always be under 4 bits, that means.
One more time, sir?
It should always be 4 bits.
Correct. You should never go any more than 4 bits. That's why it's hexadecimal, so we can chunk those and get them into that system. Okay? Does that make sense, guys? All good questions. Thank you. Okay. Let's take a look then at a longer example of this. Okay. By the way, there's no reason as to why there's a space here. I guess when I was doing it, it decided to space out. So let's just go ahead and do that. So 11001. Sorry, it's going to take me a little while to copy it. 11001, 1001, and then 1101. Both ways.
You got one too many zeros.
Oh, shit.
Yeah,
Where I'm done.
very beginning.
11001, 1001, 1101.
That's good.
Yeah, you tripping, bro. Whatever you're smoking, give me some of that.
It's in the car.
It's in the car. Nice. Okay. We'll just take a high right after we're done. Okay. So, I guess what we should do is, let's just go ahead and we're gonna convert the decimal first. So remember, with our process for decimal, we just literally write out the powers of 2. 2, 9, 2, 10, 2, 11, 2, 12.
We will need calculator for this.
No calculator. I'm kidding. Calculator. Okay. The good news is, guys, anything with a 0, just wipe it out like it doesn't even exist. Okay. So the 2 to the 1st doesn't count. 2 to the 5th, 2 to the 6th, 2 to the 9th, and 2 to the 10th. So we multiply all those by 1. Okay. So this is going to be 1 times 1, which is 1. This is 4, 8, 16. We skip 32, we skip 64. We have 128. We have 256. We skip 512, we skip 1024. We have 2048
and
and
4096.
4896, right?
4096.
4096. Okay? And from there, guys, we just add up the numbers. Okay, does that make sense,
We
guys?
can use calculators in exam, right?
Everyone else can, but you can't.
Oh,
I'm just messing with
so
you.
can I use my smartphone then? I will.
No, sir. I'm just messing with you. Absolutely. Yeah, you guys can use a calculator for the examination, absolutely. Okay. When somebody gets a sum for that, if they'd be so inclined as to tell me what the sum from that is, please. Never. Go ahead, sir.
6,497. I mean, I did it all non-calculated.
Oh, nice.
I might be wrong, but.
That's okay. I could be wrong too. Can anybody verify the young man's suggestion or answer? Not yet. Okay. When somebody verifies that or disputes it, if you guys will let me know. 6546?
6557.
6557?
No, okay.
Well, it has to be odd. It does have to be odd because the last number is odd.
I just did 6,557.
Okay,
Oh, yeah,
6557.
it's 7, I forgot
Okay.
to add the 1.
Okay, that's all right. All right, so we got 2 people that got that, unless you guys are just lying to me and one of you want the problem, which is fine. That's okay. Okay. So you're only off by 60. That's not bad. That's way better than government work. In fact, it's not government work because you underestimated. So they would have definitely overestimated. Okay.
Where does the S come from?
Oh, this is a 5, sir.
Oh, 5.
Sorry. That's my handwriting that's really bad. I'm gonna do this from now on. I'm just gonna work right with 5 for everything. I'm just kidding, I won't do that, so. Maybe I can just like get some stencils and actually learn how to write. Oh, John, I'm sorry, sir. Is that better? Okay. Other questions, guys? Okay, so that's the decimal version of this. Let's get the hex version. Okay, so all I'm gonna do is I'm gonna chunk out, starting from the right, with 4s. So I'm going to have a chunk of 1101. I'm going to have a chunk of 1001. I'm going to have a chunk of 1001 again. And then finally, I'm going to have a chunk with just the 1 as the rightmost bit. But of course we know if it's missing some bits, we're just going to fill those missing bits in with zeros. Okay, so 0, 0. And it always has 4 bits. So, does that make sense, guys? I started from the right, and I just made groups of 4, starting from the rightmost possibility. Okay. Now, all we have to do at this point is just figure out what each of those are. Okay. I'm trying to think.
199D.
Well, because I was actually going from the right book. That's fine. Okay. So I looked at this one, guys, and didn't we just do 1101 in the previous example? So unless it just changed, okay, which it didn't, this is still going to be D, okay? And that's just because it's going to be 2 to the 0 plus 2 squared plus 2 cubed, which is 13, which is D. This guy right here is going to be 2 to the 0 plus 2 to the 3rd, okay, in order, I think you said it was 9, right, sir?
Mm-hmm.
For that one. Since the previous one was 1001 was 9, I'm going to guess that the subsequent is also 9. And then finally, 0001, that's just 1. Okay, we can all see that's 2 to the 0. So 199D, okay? And then when I write my answer, I just kind of smush it together. In other words, I juxtapose that answer. That's what it's called, juxtaposition, okay? So 199D in base 16. Yeah.
Are they always gonna be the same, like you said, this, if you can remember that?
Oh yeah, that's exactly right,
You
Donnie.
can
Yup.
start memorizing them?
Absolutely. If you want to memorize those rather than computing it each time, it will work every
Now, how
single
do
time.
we, show our work for that, just say we memorize it?
Yeah, that's fine. Or you could just write the decimal version of it. Like for example, like if you saw like 1110, you would just say, well, that's 14, which is here, and that'd be perfect for me. Okay? Good.
How many combinations are there then? If you
15.
So you.
Or I'm sorry, 16. 0 through 15. There's 16 different ways that you can arrange this.
So that really isn't too difficult to memorize.
It really is.
That's how I look at it.
So that's,
Right.
so that's a realistic approach. Do you recommend that? Do you think that's a good habit to get into, to just see these and recommend?
It couldn't hurt, and I bet you probably a lot of them you're going to start recognizing just by doing the problems over and over again. Plus, think about this. Okay, Andre, what's this? In
0?
0. So you already know one of them, right? What's that?
One.
There you go. You're already what? 1/8 of the way there. Because that's, yeah, see? Victory. Good for you. But no, and I think it's valid what you gentlemen are saying, is that just by sheer, like some of them are easier, but some of the harder ones it might be beneficial to memorize.
So the zeros and the problems, like for the nines, in between, they're kind of like placeholders.
That's
for the
exactly right,
two
yeah.
to the first, but you don't really calculate that.
Correct.
through.
Yeah, because that's really, like this guy right here, this is 2 to the first times 0.
Okay.
Doesn't mean
Oh, that's why. Okay.
Right, okay. And if you want to think of it as a placeholder, that's fine. Okay. Other questions, guys? Go ahead, sir.
Is there an easy way to convert hexadecimal back to decimal, or do you have to go back to
What you would
binary?
do is you would take this, which is 13, and you would multiply that by 16 to the 0. You would take this 9, that would be 9 times 16 to the first. This 9 would be 9 times 16 squared. This 1 would be 1 times 16 to the third, okay? And that's how you can check your answer. Because each of these represents a power of 16 now.
Oh, so that's from hex to decimal.
That's correct, if you wanted to do that, okay? That's the intermediate, or that's the way to do it without going through the decimal, or the binary version.
And we always have to read from the right to left, right? Not
Yes,
from-
sir. You always start from right to left, which is counterintuitive, right, guys? Because when we read, we go left to right.
We're gonna have to go backwards. Like
No, sir, okay? I'm okay with, as long as you guys can get the binary, you can get to the other two. But no, I won't ask you to do that. Okay, does that help, sir?
Yeah.
Nice. And I bet you can do that very easily and check the 6557 if you want. Okay, other questions, guys? Okay, let's go ahead and take a look at if I wanted to convert to binary and hex. Okay. So we have our number 1, 2, 3 in base 10. Okay. Now, whatever way you guys want to do it, that's fine, as long as you don't cheat, okay? Let me show you guys the way that I think about it, okay? I start writing out my powers of 2, okay? So I go 2 to the 0, 2 to the first, and like above that you can write like 1, 2, 4, 2 cubed, which is 8, 2 to the fourth, which is 16, I hope I don't run out of room, 32, 2 to the sixth, which is 64, just would barely make it, 2 to the seventh, which is 128. As soon as I get to a number that's just bigger, okay, or that's bigger, I'm sorry, than the number I'm trying to convert, that's where I stop, okay? So I just keep writing out the powers of 2, and I know that it can't contain that bit, okay? By the way, this is going from decimal to binary, so that way we know specifically which one we're looking at, okay? So, what I'm doing is, I'm saying, okay, well, how many 64s are in 123? How many 32s are in 123 after I subtract? I'm basically just going to do continuous subtraction. Just like we did over here, we did continuous addition. I'm going backwards. So, I'm going to put a 1 under here, because I can take 64 away from 123. Okay? As long as you can subtract the power of 2 you put a 1 underneath of that power of 2. Okay? 123 minus 64, that's going to be 59, I believe. Okay? My next possible bit, 32. I know that I can take 32 away from 59. So I'm going to put a 1 under this one, and I'm going to subtract 32. 59 minus 32 is 27. So see what I'm doing, guys? I'm just continuously subtracting. And remember, in binary, there's only 1, okay? We can't put a 2 under here, because that would mean that we're in something like tertiary, which we don't want to deal with. Okay? I know that I can take 16 from 27. So I'm going to put a 1 under here. And then 27 minus 16 is 11. I know that I can take 8. Okay? So I'm going to subtract 8 from 11, which leaves me with 3. Now, I want you to notice when we get to 2 squared, I can't take 4 away from 3. So what I do is, I just put a 0 there. Okay? So basically, guys, all you're doing is you're just putting 1s in the places where you can subtract that power of 2. You put 0s where you can't subtract that power of 2. Okay? I know that I can take 2 away from that. And I know I can take 1 away from 1. And then, by the way, guys, there should never be a remainder. Okay? Does that make sense, guys? I mean, all we're doing is we're continuously subtracting powers of 2 that we can possibly subtract. Okay? It's almost the inverse operation of what we did up there, where we added the powers of 2. Now we're subtracting. Okay?
Why don't you start dividing them by 2 and then reverse it, huh? You know?
Dividing by 2?
Yeah, so what you do is, say 123 divided by 2, that's how much it comes to, then take a 1. You understand what I mean?
I see. That would give you the remainder.
Remainder, yeah,
Okay,
the
that's
mod.
Yeah, you can do a modulus version of that as well. Okay,
Yeah.
but we haven't learned div and mod,
Okay.
so I'm going to stay away from that stuff. I know most of you guys probably know what a div and mod is, but I'm going to wait until we get to proofs to do divs and mods.
So if I do it by mod, you're not gonna.
Oh, no, that's fine. Like I said, this isn't the only way to do this. This is the way that I know how to do it without teaching you guys like modulus functions or anything like that. Okay? All right. So guys, this is our number right here. It's going to be 1, 1, 1, 1, 0, 1, 1 in base 2. Now what I want to do is, like I said, once we get to binary, we're all good. Because binary is like the mediator between the two. So, now what I'm going to do is I'm going to chunk 4s. 1, 1, 0, 1, bracket of 4. 1, 1, 1, and then the 0 is a bracket there. Okay. So now what we're doing is just like we did with the other 2 problems, we're just getting into base, into our hexadecimal. Okay. I know that this is going to be 2 to the 3rd, plus 2 to the 1st, plus 2 to the 0. That's 8 plus 2 plus 1, which is 11. But instead of 11, guys, what letter do we use in hex? B, right? So this guy right here, or girl, is going to end up being a B. Okay, does that make sense to everybody, guys? Just like the other ones. And this is one where, with Donnie and Andre, I think it's good if you guys memorize those instead of like having to do that all the time. Okay? Although if you have to do it by hand, I mean, what does it take you, like 3 seconds? Okay? This guy is going to be 2 squared. Plus 2 to the 1st, plus 2 to the 0, 4 plus 2 is 6, 6 plus 1 is 7. So it looks like that instead of having to write 1, 1, 1, 1, 0, 1, 1, which is tedious, we could represent that as 7b in base 16. Okay. Right. Does this make sense, guys? Any questions about how we're going to convert back and forth? If I give you guys the decimal, okay, you guys are going to convert that into hex, or I'm sorry, to binary, and then from binary to hex. Okay? Let's go ahead and do another one together just to make sure we're okay with the process of this. Okay, a little bit larger number this time. So this time we have 975. And as you guys can imagine, this is going to be a fairly big number to try to write in binary. Okay, so let's just try to beat it out of it. So 975 in base 10. All right. What we're going to do, guys, is we're going to start with 2 to the 0, and we're just going to write up in powers of 2 until we get to a number just bigger than 975. Okay? So we have our 2 to the 0, which is 1, 2 to the first, which is 2, 2 squared, which is 4, 2 to the third, which is 8, 2 to the fourth, which is 16, 2 to the fifth, which is 32. So boy, this is going slow. 2 to the sixth, which is 64. 2 to the seventh, which is 128. 2 to the eighth, which is 256. 2 to the ninth, which is 512. And then finally, 2 to the 10th is 1024. And we stop with that. And by the way, guys, if you have your powers of 2 memorized, you don't have to write up the numbers above it, okay? I bet you a lot of you already have like your powers of 2 memorized up till like, you know, probably like 9096 or whatever it is, or 4096. So I'm not going to give you guys like ridiculously huge numbers, okay? I'm not going to give you anything in the millions or hundreds of thousands, okay? All right, so now what I'm going to do is I'm going to start at 512, because that's the number that's just smaller in binary. I'm going to put a 1 under that. We're going to subtract 512. And that's going to leave me with 463. Then I'm going to take 256 away from that, because I certainly can take 256 away. So if I do that, I'm going to wind up with 207. By the way, you should never get a number that's bigger than what's left over there. Okay? If you do that, that means either means A, you made a calculation error, or B, you just didn't go up high enough, or you skipped a power of 2. Okay? It never works out that you have like leftover stuff. Okay? We can take 128 away. So minus 128, and that's going to be 79, I believe. Okay. And then we can take 64 away from that. So we're getting there. Okay, this one's going to be nice. So that leaves us with 15, I believe. Okay? And that means that we can't take the next 2 bits away, because 32 is bigger than 15. 16 is bigger than 15. So I'm going to put a 0 under here, because I can't take it away. I'm going to put a 0 under the 16. And then I know I can take 8 away from 15. That leaves me with 7. I know I can take 4 away from 7, which is 3. I know I can take 2 away from 3. And I know I can take 1 away from 1. And by the way, this is the way the computer has to do it, okay? The computer can only think in very, very discrete terms of whole numbers, all right? So, unfortunately, this is fairly tedious for us to do as humans. Computers do it very, very easily. Okay. So, if I was looking at a number in base 2, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1. It's a palindrome. Nice. Except the binary palindrome. Okay. It looks like an emoji that like somebody's looking out from prison bars. So like if you're ever incarcerated, that's like the I'm in jail sort of emoji. Like here's the 2 eyes, and then here's all the prison bars. Alright, so just saying like if you ever get in jail, that might be good if you want to text somebody like, lol, I'm in jail, 1111001111. So, good stuff. Alright. I think the next thing we probably want to do is we probably want to convert this back into our decimal version. I'm sorry, hex version. So to get to the hex version, 1111 block, 1100 block, and then finally a block of 11 with a couple zeros in front. Alright guys, at this point, we just do our conversions, okay? So I have 2 to the third plus 2 squared plus 2 to the first plus 2 to the 0. 8 plus 4 is 12, 12 plus 2 is 14, 14 plus 1 is 15, but instead of 15, we use what letter?
F.
F. Very good, okay? And you guys know, if it's all ones, it's 15 anyway. There's no number that's higher, okay? So we use F. And then this is going to be 2 to the third plus 2 squared, which is going to be 10 in hex. What do we use, guys, instead of 10? A. Very nice.
I think it's
Is
12.
it 12?
Oh yeah, it's 12. I'm sorry. So you are right, it's going to be 10, but we're going to use C as the right letter, right, guys? Because this is going to be 14. I'm sorry.
12. There you go.
I wrote the right letter up there, right?
Yeah.
Sorry, guys. Okay. And then finally, the last one, that's going to be a 3. So we just have 2 squared. Oh, I'm sorry, 2 to the first plus 2 to the 0, which is going to be 3. So this guy right here is going to convert to 3CF in base 60. All right. So, questions I can answer for you guys about how we're going to go through and convert these out. Okay, not meant to be too difficult. Okay, just making sure that we're all okay with it. Okay. Last thing that we want to do is we want to convert these guys into binary and decimal. Okay. But I'm guessing you probably have a good idea as to how to do this now. That we've seen a few examples. So let me just go ahead and do the first one. Okay, just because I feel like since we've seen like the conversions, you guys are probably going to be really good at the rest of it. So I have A, 2, 5, and base 16. Can somebody tell me like a process that they might utilize to get to the other 2 number bases?
So you have to separate all 3 of them and make it by 4, like this.
So maybe like this, okay. And you're saying like take those 3 hexadecimal characters and convert them into,
Like decimal or?
not decimal, but
Binary.
binary, right? We
Uh-huh.
always want to go to binary if we can first.
Okay.
So yeah, I think that's a good approach. Unjuxtaposition, if that's a word, all right? If it isn't, I just made it up, okay? So 5. If I want to convert 5 into binary, okay? What permutation of bits, of 4 bits, is going to give me 5 in binary?
1, 0, 1.
1, 0, 1, 0, 1, right
0,
guys?
0, 0.
Okay. Does that make sense, guys? That's going to be 4 plus 1, which is going to be 5. Okay? What permutation of bits is going to give me 2?
0, 0, 1, 0.
0, 0, 1, 0, right? All we just need is the second bit turned on. So 0, 0, 1, 0. Everybody see how that works, guys? Any questions? Okay. And then A is 10, which I believe is going to be 8 plus 2. At least this time it is 1, 0, 1, 0. So I finally got one right. Okay. Sorry about that, guys. And then from there, all we do is we just juxtapose those together, and we just get our binary number, okay? So in binary, this is going to be 1010, 0010, 0101 in base 2. Does that make sense to everybody, guys? We're just breaking it up. And then for the other part of it, guys, don't we just write out the powers of 2, and then we just add them up, okay? This is the easiest thing to do, because this is the decimal stuff, okay? So this is going to be 2 to the 0, plus 2 squared. We skip 3, we skip 4, we have 2 to the 5th. We skip 2, 6, 2, 7, 2, 8, we have 2, 9. We skip 2, 10, and then we have 2 to the 11th. So you could literally just punch that into your calculator and get a sum out of that. That might be the easiest thing to do, rather than figuring out what 2 to the 11th is and adding it all out. Okay. So when somebody gets a sum for these, if they'd be so kind as to let me know what they got for their sum for those 5 characters or those 5 bits, please. So
$2,597.
2597, okay? Yeah, I mean, that looks good to me, because this is gonna be your 2048, and then that's gonna be your 512, so yeah, it's gotta be like almost 2600, so that looks viable to me. Can somebody confirm that,
Yep,
just to make
you're
sure?
right.
Okay, thank you, gentlemen, I appreciate it very much, okay? That's gonna be our base 10, and we are done with this. All right. So, the whole purpose of this is for those of you guys that are going to keep going in computer science, and if you're doing some work with like computer architecture or computer algorithms or processing, you might have to do some conversions like this somewhere to be able to work with the memory, okay? So I just wanted to make sure that you guys had this skill and you knew how to do it. Although quite honestly, if you had to do it in real life, what would you guys probably do? Just type it into Google, say, Google convert 2597 to decimal or hexadecimal or whatever it is, and it would do it for you, okay? Not saying to do that on the homework because you won't get any credit for that, but you could check your answers certainly, okay? I have no problem with you guys going into Google and just checking to make sure your answer is correct, okay? Except on the exam. All right, questions I can answer, guys. We feel okay about this stuff, just number tricks, right? We like number stuff. It's just when we start having to throw integrals and stuff, that's when life gets terrible. All right. So the other thing I wanted to look at this afternoon was I wanted to look at this thing called 8-bit addition, okay? So I have two different things. I have computer representation of negative integers, and then I have the 8-bit addition. So let me really quickly talk to you guys about how computers represent negative integers. Now, we're only going to stay from between negative 128 and positive 127, okay? So this is like the most fundamental process. This is when you start getting the full adders and you start throwing more full adders together, okay? And it also becomes multiple 8 bits of addition, so. All right, so if I have 8 bits, so 8-bit representation, first of all. The way 8-bit works is that you start at 2 to the 0, and surprise, you're going to have 8 bits. 4, 2, 5, 2, 6. Except the 8-bit is a sign bit. Okay? So, every time a computer wants to store a number, okay, that reads between the numbers of negative 128 and positive 127, okay? This is what it does, okay? It basically has registers, okay? Sort of like assembly programming, okay? If any of you guys have suffered through assembly so far, okay? Yeah, pretty nasty stuff, right? Oh well. Yeah, it was the same thing back in the 90s, so it's still worthless anywhere. But unless if you write like a program in assembly, it runs ridiculously fast, although nobody ever writes programs in assembly anymore. But regardless, all right? This is basically going to say that it tells me what the sign of the number is, and then it just adds up these numbers, okay? So if it's a 1, that means you're dealing with a negative. If the sign bit is a 0, that means you're dealing with a positive number, okay? So the first thing a computer does, let's say it wants to print the number negative 64. First thing it does is it reads the sign bit and decides whether it's positive or negative, and then it actually prints out either negative or nothing. Then what it does is it uses these and it adds up the power of 2 and it spits out the number. Okay, so that's actually how a computer prints out negative numbers. All right, let's say for some reason, okay, I wanted to represent the number negative 13. Okay. All right, here's how I represent negative 13 in decimal using this. Okay, I'm going to go ahead and I'm going to use this 8-bit method right here. Okay, so I have, and I'm just showing you guys how I represent negative integers. So we have the sign bit, 26, 25, 24, 23, 22, 21, 20. And by the way, this is negative 13 in base 10. Okay. Now, a computer can't decipher unless it looks at the sign bit if the number is positive or negative. Okay, so here's what the computer is going to do. If it wants to convert it into binary, it's going to start by leaving the sign as 0. Okay, even though it's negative. I know what you guys are thinking. you guys are thinking, well, if it's a 1, it should be negative. But when it reads it in, it's going to read it in as a 0. And then all we're going to do is we're going to represent 13 without resolve of the sign in here. Okay, so 13 is going to be 8 plus 4 plus 1, right? So that's 13, so 8 plus 4 plus 1. Okay. Now, you guys would agree with me that that is the binary representation of 13, right?
Mm-hmm.
How does a computer represent negative 13? What it does is it takes something called the 2's complement. Okay, so since it's negative, we're going to take something called the 2's complement. What the 2's complement is, you just change all the 1's to 0's, all the 0's to 1's, and then you add 1 at the end. Okay, so 2's complement, the 1's go to 0, the 0's go to 1, and then you add 1 at the end. Okay, so that's what a computer does to distinguish between negatives and positive. It changes the parity. Okay. So let's just go ahead and do that and see what happens. Okay. If I change all the 0's to 1's, I get 1, 1, 1, 1, 0, 0, 1, 0. But then I have to add 1 to this guy, right? So really, you guys are right, what I'm ending up with is 1, 1, 1, 1, 0, 0, 1, 1. Okay? And this is the way, in 8-bit addition, that a computer recognizes that. Okay? It doesn't want to have 2 different registers, if you would. It doesn't want to have a register for negatives, it doesn't want to have a register for positives. Okay? It just wants to have 1 register for numbers. Okay? So what happens is, the computer reads this. And the computer says, oh, okay, well that sign is a 1. That means I have to take 2's complement, and then I have to print out a negative to start with this. Okay? So that's the way the computer reads this. It's the algorithm that it has. Okay? Remember, guys, when computer science was developed, memory was an extremely scarce resource, right? I mean, think about how much. Have you guys ever seen the pictures of a supercomputer or anything like that? How big are supercomputers?
Bigger than
This
this room.
room, right?
Yep.
And how long does it take a supercomputer to crunch out like a small program? Like maybe a day? Okay? Think about like how many times, like if you expand like the number of registers and the pockets in a computer, like how much time that would take. And by the way, that's if you did everything right. If you did something wrong, you go away for 2 hours or 3 hours or 4 hours and then come back and try it again. And by the way, you didn't even know what's wrong because they didn't have decoders like they do nowadays. So.
Question. Since technology has evolved so much, then why are you learning this thing?
Well, that's a good question, okay? Question is, how come, since technology's evolved so much, how come we're still doing this? Because it still makes the runtime faster, okay? And think about this, guys. How impatient do you guys get when you click the internet and you gotta wait 2 seconds for it to load? I wanna choke somebody, literally. Somebody bad, not you guys. You guys are all good, okay? But I wanna choke somebody bad. Now, think about doubling that time to 4 seconds. Then you want to choke them and punch them at the same time, as dark as that is. You don't record that, by the way.
Okay.
Whatever, I don't care. Can't fire me. So, but that's why. It's just because the memory runtime is so valuable to us. Okay. Think about this, guys. 2 things you can never get back in your life. Okay. You can't get back respect. I mean, you know, if you base somebody and it's not true, then you can't get that back, and you can't get your time back, right? Like if you lose your money, you can get your money back. Okay. But you can't give back time, and I think that's what's happening is that as we're evolving as humans, we're realizing that time is the most valuable commodity, okay? I think that's one of the reasons why we don't, okay? Anyway, that's more philosophy, and we don't deal with philosophy in this class. All right, so does this make sense, guys? Any questions about how we represent negative
I just
integers?
have one singular question about it. At the end here, it's a 0, so when you add the 1, it turns into a 1.
Correct, right.
If it was a 1 and you added the 1,
Then you would carry
it goes to the next.
Right, right. So, like for instance, if you added 1 plus 1 in binary, that's 10. This is the sum and this is the carry digit, okay? So you would actually have to do
Oh, so
some
you put
carry.
it in front of it
Correct.
rather than behind it.
Just like if you added 7 plus 3 in decimal, you would put the 1 up in top and you would add that.
So with this number, will the 1 move all the way to the 2 to the second?
Correct, right, so if this was a 1 plus 1 would be 10, carry this 1 plus 1 would be another 10, 1 plus 0 would be the 1, right.
Okay, so you would have 1, 0, 0.
Correct, sir. And we're actually gonna do plenty of examples of this, just to make sure you guys see that in practice. Okay, good question, thank you guys. Okay?
So what's the advantage on doing that versus just flipping the sign bit?
Oh, because I see what you mean, like putting the 0 there, it's still, that means you have to have 2 different registers, I think. And when you start getting bigger and bigger numbers, then it starts getting more and more expensive.
I got a question.
Hold on a second, let me make sure he's okay with that. Is that okay, or?
It's just how the computer works.
Yeah, it's just how it's worked forever. And I know, it's like, sometimes that's not a good answer, but think about trying to reprogram everything in that. Everything, ever. Yeah, I know. And it's so much more convenient to do it the way that you're thinking about. It really is. Okay, but
It'd be slower.
it would be a lot slower, yeah, runtime, unfortunately. So quite honestly, it's all about runtime. So, go ahead, sir.
Okay. So after 2's complement, we suppose we have a somewhere, we have all of them as 1, and then we add 1 extra to it. So is there going to be shift by 1?
If for some reason you have an overflow, you just get rid of that overflow. You truncate it. Okay?
I'm not getting you. Who truncate what?
The extra one. Like, are you saying like if we just kept adding 1, 1, 1,
No,
1,
no. I'm saying let's say the 2's complement. We did 1, 1, 1, 1, 0, 0, 0, 1. Like, so over here, if all of them were 1 on
Yeah.
the 2's complement, and we add 1, so shouldn't that thing go shift by 1?
Oh yeah. Like there'd be a 1 all the way out front and everything's a 0.
Okay.
But that 1 would actually go away.
Okay, go on.
So we're going to do some examples of where you do get that overflow and you truncate it.
Okay.
Okay? Go ahead, sir.
So, let's say you want to go from negative back to positive, you would just subtract 1?
What you would do is you would just do the same thing. Okay? So if you take, anytime you take a 2's complement, you change all the bits and you add 1. Okay? So if you want to take the 2's complement of a negative, you still do the same thing.
So you still add 1,
Yes.
but then would it be 1 higher?
No, it'll still be the same thing because you're flipping the bits and there might be overflow at the end that compensates for that.
It goes both ways.
Right.
Alright.
It'll work out. So I'll prove to you it does work out.
Take your word for it.
That's okay. It might be one of those things where after we work a few examples, you can see like the intricacy of it. And I see what you mean. Like you're thinking inverse function,
Yeah.
but it's not necessarily a function because there's not a one-to-one relationship between a negative number and those 7 bits that are to the right. Okay? Because it's not really a function, it's a relation, because this could be a 1 or a 0, meaning that this number right here has a different positive and negative number when you flip it over. Okay? So it's not necessarily a functional relationship.
Yeah.
Okay? Alright, other questions, guys? Alright, let's try to kick a few of these out. Okay, so let's start off with a really easy one. Okay? All I want to do is add or subtract, okay, and I want to use only the 8-bit representation. Okay, so I have 89 plus 55. I'm going to change that because that answer gives us a number bigger than 128, and I don't want to deal with that because then you need another 8 bits to represent it. So if you guys would, instead of making that 89, let's make this into just 69, because that'll give us a number that's just slightly lower. Plus, who doesn't like the number 69? Bill and Ted love it, so good enough. All right. So here's the way I think about this, guys. Okay. So we start off with our sign bit. Okay. And then we have 2 to the 6th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st, 2 to the 0th. Okay. All right. I'm going to take number 69 and I'm going to take number 55. Okay. And no matter what, the sign always starts out at 0, no matter what. So if it's positive, it's 0. If it's negative, it starts at 0, no matter what. Okay. What I need to do is I need to represent 69 in binary. Okay? I think we can represent 69 in 3 bits. Okay? What 3 powers of 2, or what 3 powers of 2 could we add up to be able to get 69? obviously 64, right?
Mm-hmm.
So that's 64 is that one. If we subtract 64 from 69, that leaves us with 5, right? Which is what two numbers in base 2?
Basically, it will be
4 and
4
1,
and 1.
right? So we would just add 4, and we would add 1. Okay? Or, if you guys wanted to, remember the process that we just used? You would just continuously subtract, okay? I just always think to myself, what permutation gives it to me? Because we're dealing with smaller numbers, okay? But is everyone clear, like, that 64 plus 4, or sorry, 64 plus 4 is 68, and then one more is 69, and I'm just going to fill in zeros for the rest of it. Which is actually sort of the same process that we just used. Okay? Now 55 is a little bit tougher, right? So 55, I can't take 64 from that, but if I take 32 from 55, that leaves me with 23. If I take 16 from 23, that's 7. Can't take an 8. If I take 4 from 7, that's 3. If I take 2 from 3, that's 1, and that's 1. Okay? So basically, guys, what I just did was, I just did the process in my head where we converted the binary, or the decimal to the binary stuff. Okay? I just did it expediently just because I wanted to save time doing that. Is that okay with everybody, is how I did that, guys? Just do it in your head. Or, if you need to write it off to the side, that's fine too. Okay? Now, here's what I'm going to go ahead and start doing some of the carry stuff, which is what you gentlemen were talking about. Because it's pretty obvious we're actually going to have several carries, right guys? So, we're going to add these numbers together. Okay, because that's what we're doing, is we're taking our binary numbers we're adding. 1 plus 1 is 10, but I don't want to write a 10 here. What I'm going to do is 1 plus 1 is 10. Okay, so see what I did there, guys? I know it's 10. I put the 0 down here, and the carry is a 1. 1 plus 0 plus 1. I can't have 2, I have 10. Okay? So, does this make sense, guys? All I'm doing is I'm just adding them. And then, because I can't have 2 characters in the same space, I'm carrying it over. Okay? What about 1 plus 1 plus 1 in binary? What's that, guys?
1.
11, right, guys?
Mhm.
So we're going to have 11 here. 1 plus 1 plus 1 is 11, so I put a 1 here, and I put a 1 up there. Does that make sense to everybody, guys? We're just adding the bits. Anything bigger than 1, I'm going to have a carry. Okay, so I just carry a 1 up top. 1 plus 0 is 1.
1. Okay.
0 plus 1 is 1. 1 plus 1 is 1, or 0 plus 1 is 1. 1 plus 0 is 1. And then 0 plus 0 for the sign bit is 0. Okay? And by the way, when I say 8-bit addition, this is how the computer has to do addition. Okay? It doesn't know anything else. And then also, it goes through the logic circuits. And I showed you guys like the full adder and the half adder. Just a whole bunch of those full adders put together. Okay? So, and the reason I do this is for those of you guys that are comp sci majors to get an appreciation of how hard the computer works to do this. It really is a very difficult process. Okay, so last thing a computer would do is, okay, it would spit out your answer, right? To spit it out, doesn't it convert it back into decimal, right? So let's do that. Okay, so last thing it's going to do is going to convert back. Nothing here, nothing here. Okay, this is a 2 squared for this guy. To the 3rd, to the 4th, to the 5th, and to the 6th. Okay? So, if you guys would, just go ahead and add those up. And if somebody can tell me what the answer is to that sum, or you just add the numbers to get 124, I guess.
Yeah.
Yeah, that'd probably be the cheater. That's the cheating way of doing it, but, you know,
The computer has to do it this way.
that's exactly right.
So that people don't understand.
Yeah, okay. But if you add these up, it should give us 124 in base 10. Okay? Now, this is what a computer knows in base 2. Okay? But remember, humans and computers are different. Computers think in base 2, humans think in base 10. And quite honestly, the computer's there to serve us.
So at the very beginning, or I'm sorry, at the answer, and then you added the 0 up in front of everything.
That's the sign. That's 0 plus 0, which is 0.
Oh, okay.
Okay? Okay. There we go. I just discounted the sign bit because I knew it was going to work out like that. So, sorry. Does that maybe help out now, sir?
Well, yeah, I just figured, I mean, I guess the sign makes more sense than I
Right.
just put like 2 to 7, because
Right.
if you were to have 124, you need that extra.
Right. And by the way, you do have to have this, okay? It's 8-bit addition, so don't cheat yourself. I know like sometimes you have smaller numbers, okay? But make sure that you guys are using all 8 bits for this. Okay. So does this make sense, guys? That's what a computer has to do with positive numbers. Now what happens when we start having some negative numbers? That's where we start having to throw in that 2's complement. So let's take a look at a secondary example. Okay, so we're going to have 53 plus negative 102. So, we have our sign bit. Sign bit always starts out at 0 no matter what. We have 53, and we have our negative 102. And then we have 26, 25, 24, 23, 22, 21, 20. I'll give you guys a minute to copy it. So, no matter what, guys, if you write this on the test, you at least get a point for doing that, okay, without even doing any sort of calculations. All right. We have to somehow get 53, okay? So, to me, 53 is just 2 less than 55. So, wouldn't 53 be the exact same number here, except instead of 2 to the first is a 1, it would be a 0, right, guys? So I just like to borrow stuff if I can. So it'd be 0, 0, 1, 1, 0, 1, 0, 1. Okay. So for 53, 0, 1, 0, 0, 0. Wait.
Yeah. 0, 0.
I'm looking at, oh, okay, 0, 0. Wait. What am I looking at? I'm looking at the 69. Okay, that's why. So 0, 1, 1. Hey, that's not right.
I did this. You want me to tell you? 0, 0, 1, 1, 0, 1.
Well, oh, okay, 0, 0,
Uh-huh.
1, 1.
0.
Okay, 0, 1, 0, 1.
Uh-huh.
Yes.
I don't know, I kept starting to look at like things and
So
started going
you're
crazy.
looking at the signs as well too.
Yep, that's what, you're right, Donnie. Okay, thank you guys. Alright. Now, 102, we're just going to do the same thing, but we're not going to consider the negative yet. Okay? So, I know that I need 64. Okay, so when I subtract that from 64, that's going to be what, guys? 38. And then 38, 64, yep. And then to get 38, that's going to be 32 and 6. So it's going to be 2 plus 4, which is 6. 6 and 32 is 38. 38 is 64. That should be 102. Is that correct, guys? Can somebody verify? Yeah.
0,
Sure, why not?
1, 1, 0, 0, 1, 1, 0. Yep.
Yeah, that looks good. Okay. Yes, sir.
So, will we ever, since it is 8-bit, we won't have to deal with numbers larger than?
Correct. I will not give you numbers or answers that work out to be anything less than negative 128 or bigger than 127. Okay?
Sorry, why is the sign bit not 0?
We're going to change that in a second. Okay? Yeah, that's a good question. Okay? So we start with 0, but remember, anytime we have a negative, we're going to take the 2's complement of that. Okay? So this guy right here, since it's negative, we're going to take our 2's complement of this. Okay? So the 2's complement, we just flip the bits and then we add 1. So it's going to be 1, 0, 0, 1, 1, 0, 0, 1, and then we add the 1. Okay? So that's what a computer does. It says, okay, well, I'm going to remember that the first thing that I encountered was a negative. So instead of having a separate register for this, I'm going to go ahead and just use the 2's complement. Okay? If we add this, 1 plus 1 is 10. And then the rest of it we just carry down. Okay. So, is this okay with everyone so far? Any questions that I can answer? If for some reason you have a negative, Okay, first thing you guys do is you just write out the number, okay, without the sign, then you take the 2's complement of that negative number. Okay. Now what we're going to do is we're going to take the 53 and the 2's complement of negative 102, and we're just going to add those two binary numbers together. Okay, so I'm going to take our 53 and our negative 102. 53 was 0, 0, 1, 1, 0, 101. Negative 102, I'm going to use what's in blue here, 1001, and 1010. Let me get it, guys. Right, sorry. And all we're going to do, guys, is we're just going to add those two together. Okay, so let's go ahead and add them. 1 plus 0, 1. 0 plus 1, 1. 1 plus 0, 1. 0 plus 1, 1. 1 plus 1, we finally get to a 10, so we're going to have to carry. 1 plus 1, another 10, so we're going to have to carry. 1 plus 0 is 1. 0 plus 1 is 1. Okay? So, that should be what the computer adds 53 and negative 102 to read. Okay? And what the computer says is, okay, well the first bit's a negative, so I can easily see that, or the first bit's a 1, so I can see the answer is going to be negative. Now, what the computer has to do though, is it has to print it out. Okay? So, before we do the last part of this, is everyone okay so far? Okay? The only difference in this problem is we just took the 2's complement of the negative, and then we added the 2's complement with the positive. Okay? Now, let's say the computer wants to print this out. Okay? What it's going to have to do is, because the sign bit is a 1.
Let me report a negative.
Okay, so sign bit equals 1. That means that we have to take the 2's complement of that number. Okay? So if you guys ever get your answer, and you want to assume that the computer has to print that, which of course we do, okay? What we have to do is we have to take another 2's complement, and then the answer will be negative. Okay, so sign bit's 1, we're going to take one more 2's comp, and of course we're going to check this answer, right guys? I mean, there's a lot of stuff going on here, so we want to verify that the answer is correct, okay? And maybe this will help you to justify in your mind that it actually does work. Maybe not. Okay, so guys remember, take the 2's complement and just flip the bits. Okay, so this is our 2's. So this is going to be negative 0, 0, 1, 1. 0, 0, 0, 1. And what I'm going to do is I'm just going to tack that 1 in. Okay? So all I did there, guys, was I just took the 2's complement. I stuck a negative out in front of there. Okay? Just to remind you guys that the answer is going to be negative. So the answer is going to be negative 0, 0, 1, 1, 0, 0, 0, 1. And that's in base 2. And probably what we should do is we should check to make sure that that answer does indeed add up to, what should it add up to? Negative 49? So let's hope that it does, otherwise we just wasted a whole bunch of time in our
It
lives. Okay? So, this is going to be 1. We skip 2, 4, 6, I'm sorry, 2, 4, 8, 16, and then 32. 32 plus 16 is 48. 48 plus 1 is negative 49.
So,
And that should be, indeed, the sum of those two numbers.
so whenever you do 2's complement, you will have to add 1, even when you're converting.
Correct. Right. Okay. And remember, because it's negative at the end, you're actually getting rid of that 1 once again with it. So, I don't know if that helped out a little bit to see, at least you see it works. Maybe not why it works, okay?
Understand a little bit.
Yeah, it's difficult to see, I think, and I don't think I'm giving you a good explanation. So please blame it on me, I'm fine with that. So-
And then you add the 50.
Okay, so guys, any questions I can answer about the 8-bit addition for you all? Okay, so here's what I'd like for you guys to do, okay? Why don't you guys take about 5 minutes, see if you guys can do the last one, Okay.
Number 15.
Yep, negative 15 plus negative 46. Okay. This is exactly like a test question you guys are going to see, so now's a good time for you guys to get some practice. While you guys are practicing, I'm going to give you back your assignments, so that way you guys have those. And I'm sorry I don't know everyone's name. I will eventually get to know your names, and I will eventually butcher your name, because, well, that's why I studied math. So sorry if I butcher your name. Mr. Ahmed. Yeah, that was great, wasn't it? Sorry about that.
It's okay.
So I have Greg V. Okay. John, can you write that? So we
Also, turn into like an airplane, paper airplane.
Oh, no, I'm not an engineer. I'm just a math guy. Okay. Dave Johnson. No Dave today. Paul Rare. By the way, these were very good, by the way. So I didn't have a problem with anybody's assignment, so I didn't structure or anything like that. So Ryan Burmeister? Okay. Lucas?
Yes.
There you go, thank you.
Sure.
Adam Embers?
Yeah.
Thank you.
Muhammad? Okay. And I'm not even gonna try to pronounce it because I'll butcher it, so nice job, thank you. Greg Smith? Lauren Winnig? Okay. You're so chipper. I'm right here. There you go.
Right now, you just took the initial part of two compliments.
John Zorsky? Zagorski, I'm sorry. See, that's why I studied not English. Oh, Polak too, yeah. Except Jones is usually in Polish. I got married into that one. Not that I took like someone else's last name, never mind.
Or you
Cheyenne?
just imagine, okay.
Did I pronounce it right?
Yeah. One
Okay.
one is
There you go.
taken out.
Nice job.
So that's when, so that's
Marvin?
the one.
Okay.
And then everything else will go down.
Good one.
So this is the original.
And then John Doe?
I took one two's complement. This line right here. So obviously 0, 1. Vice versa. So all those were right there. And then I ended up with
Christian Andrews?
Yeah. I have to add that one. So then I did what this one.
Daniel Schwartz?
1, 0. That 1 plus 0 would then be a 1. And everything else would carry down. 0 carries to 0.
Hey, one of my
down.
friends. Getting better. Angeliki?
Yes.
Did I pronounce that correctly?
And then
Okay.
you'll do 1 there.
Good job.
Okay. Carry 1.
And Jacob Hurts?
Yep. And then there's nothing else. Everything else just transfers down there.
Sure.
So
Taylor?
this one will go down.
Stupid little
So
friends.
that is your final negative.
Natasha? Did I
So now
pronounce it
you
right?
want to do math.
Not even close.
53 plus that final one. So then
Taya?
take care of that.
Mashiach,
And then
okay,
whatever
so it's
you do,
actually
you
hard to
just
see.
Imagine yourself
There you go.
walking out
Good
just
job.
2 lines and be like, okay, 1 plus 0.
Michelle?
1. Okay. This is negative 1, this is negative 1.
And then Mr. Weber, last but not least. There you go, sir. Good job.
See, my problem is that.
Okay. This is very easy. 0, 1.
That's your way of showing yourself.
Oh, yeah, sorry about that.
That's okay, I just,
I feel really bad. And it wasn't even any wrong in it either.
Oh,
see, that's even worse.
If you want, what I would do, guys, is if you made an error or if you wanted to know why something was wrong, I posted the solution, so just go online and check the solutions. If you feel like I marked it wrong, when you were right, just bring it up to me and say, hey, Chris, why did you mark this wrong? Or something like that, and I'll tell you guys why, okay? But I mean, they were all really good. I didn't have any problem with anybody's work.
But now, it's just complement plus 1 at the end of that. Just change the 0 into a 1. So your final code.
Chris,
That's correct. So you can get
Do not insert.
Chris.
Alright, that's last line. Yeah, I did.
Okay, this is what I was telling you. It become 9 bits.
Right. So after this,
Okay, just test. Oh,
we truncate.
okay. Now I do the 2's complement and add 1, right?
You got it, and then you're done. If you guys get any overflow, like if you get more bits after the sign bit, just get rid of those, okay? That's called, that's just truncation, okay? Just an
I
overflow.
think it's gonna take.
So 3 ones on each bit just means 1.
Yeah.
That's it.
It's just a process.
Okay, guys, we only have a few minutes left, so I want to make sure that we have it, we see how to finish this, okay? So, can somebody verify, okay, just to make sure I did this correctly in my head, okay? Are these two initial conversions to binary correct, the 15 and the 46? Do they look okay to you guys, or anybody dispute those?
1, 1, 1,
Okay.
1, 0, 0,
And then the other thing I did was I took the 2's complement of both 15 and 46 because they're both negative, okay? So for my 15, I got 1s and then all 0s except for the last one. Okay, so does that look okay to everybody? And then for the other one, 1, 1, 0, 1, 0, 0, 1, 0. Okay, so anybody dispute either of those, or does those look okay to everybody? Because obviously I don't want to go on if I can't do addition and subtraction. Okay. So, a number of you guys, when you were going around, you told me, hey Chris, what happens if you get more than 8 bits, okay? And you were kind of worried about that. And the good thing is that should actually happen in this problem, okay? So, I'm going to go ahead and add these. 1 plus 0 is 1, 1 plus 0 is 1, 0, 0, 0, 0, 1 and 1 is 0, or 10. 1 and 1 is 10. 1, 1 and 1 is 11. 1, 1 and 1 is 11. And I think what you guys noticed is that you got this 9th bit right here, okay? Guys, if you ever get more than 9 bits, you just truncate those. That's just overflow.
More than 8 bits?
Yep, or did I say more than 9? Okay, I meant more than 8, I'm sorry, duh. Yeah, if you get more than 9 bits, that's really bad in 8-bit addition. So that's terrible. Okay. So, all you guys do is, after you get to the 8-bit, just get rid of it. Okay? Now, there's one more thing that I still have to do. It's because this is going to, if the sign bit is a 1, okay, that means you have to take the 2's complement. Okay? So, I'm going to take the 2's one more time. It's going to be a negative 0, 0, 1, 1, 1, 1, and then 0, 1 if I add the 1 to the end. And then just to make sure that's correct, shouldn't that add up to negative 61 if we've gotten that correct? Let's see if this does add up to 61. So this is going to be 2 to the 4th, or sorry, yeah, 2 to the 5th, plus 2, 4, plus 2, 3, plus 2, 2, plus 2 to the 1st. Okay? And 32 and 16, that's going to be 46, and then 46 and 8 is going to be 48, and then 48, okay. So it's 56, 60, and then 61. Okay, that's what we said, right, negative 61. So, okay, so it does work out. So that's negative 61. All right. So, oh, yes ma'am, I'm sorry.
Can't we just, because they're both negative, can we just skip that one step, add them together, and then?
Right
do the
here?
complement?
Unfortunately, you have to show how the computer would think about it.
Okay.
Sorry, like, we could do that, but a computer's not smart enough to do that, so. So the good news is, you guys are all smarter than any computer right now. So. All right, so, questions I can answer for you guys. Okay, so remember guys, assignment number 2 is gonna be due next time, so make sure you guys try a few of these, okay, and if you need some help with, make sure you ask me for that help, okay? One more, while you guys are packing up, you can keep packing up, it's fine. I did put together a list of suggested problems up through chapter 4 or 5. I'm gonna post that on Blackboard. I was literally in my office doing it right before class and I forgot to post it. So, and I know some of you guys have asked me for more problems, okay? So I got plenty of problems for you, at least math problems. I'm not making you like problems, okay? All right, so I will see you guys on Wednesday.